Hello everyone. In this video we will discuss the principal component analysis, principal component analysis, and also it is also known as KL transform. KL transform. Okay, so let's see actually what is this KL transform or PCA. Okay, that is one is this is part 1 of this topic, you know, principal component analysis. Okay, or this KL stands for Karhunen-Loeve transform. Okay, so these transforms are there. So my first query about this transform is that why we use these transform, what is the need of this. Okay, see, what is the main important need of PCA or KL transform is this. Let's say I am giving you some vectors A, B, C. This is my first vector, D, E, F, G, H, K, L, M, N. Okay, I am means I gave you these 4 vectors. Okay, x1, x2, x3 and x4. Now these x jointly I will call this as x. Okay, x. So this x belongs to, let's say, Rn. Okay, Rn. So this is not like Rn. Okay, means these A, B, C, D, E, F, G, H, K, L, M, N all are real numbers. All are first of all real numbers, and the dimension of this vector x, okay, is basically 3 cross 1. Okay, because 3 rows are there, 1, 2, 3 rows and 1 column. So the dimension of each of these x1, x2, x3 is basically 3 cross 1. Okay, 3 means rows, how many rows are there, and 1 means columns, how many columns are there. So if you apply this transform or principal component analysis to these vectors, okay, so what will it actually we can convert, we can reduce the dimension of these features, or let's say I am saying features because in AI we generally deal with the feature vectors or all this thing, but you can say vectors also, there is no issue. Feature vectors or feature or vectors. So my aim after transform, what is the advantage is that we can reduce the dimension, means we can make these x prime, okay, from x which belongs to Rm, where m is what, m is less than or equal to n. Okay, the dimension of the transformed vectors is less than or equal to n, and it is actually the actual dimension of the original features vectors, okay, or original vectors. So now this x prime can be something like this. Let's say I am considering n is equals to 3 in this case, so I am considering m is equals to 2. So I can write something like this. So n, let's say, okay, Let's say this is P, because this P is confusing. P, and this is Q. Okay, this is Q. Don't take this Mn as this, because Mn is related to dimension, and that's why I wrote Q and P. Now I will create the transform vectors is like this: A, B, where this A is not equals to B. Okay, in general it is not equal to B, but by coincidence it can be equals to, it can be equal, but in general these are not equal, not necessarily, not necessarily. है ना, not necessarily, कभी कभी they sometimes they can be equal, but in general they are not equal. So I have created the reduced dimension space, which is now 2 cross 1, C, D, E, F and G, H. Okay, each of these dimension 2 cross 1, 2 cross 1, 2 cross 1. Okay, so what I will call this as, this is actually x1 prime, this is x2 prime, this is x3 prime, this is x4 prime. Okay, now you must be wondering, there are 2 questions. First of all, how we can do this? This is first question, question 1, and question 2 is what is the need, why we are doing this. Okay, so let's discuss the second question first. Okay, see, in sometimes actually in more often we work on our personal laptops, computers, PCs are there. Okay, and we know that in AI, to handle big data, a large number of data, we need high computation to make a model in early time, correct? So in that case, if you give the higher dimensional data, means if the dimension size of the features is high, then obviously your computer will need more time and computation power to make a model or to process that data. It will take more time, correct, and more computation. But if you reduce the dimension, from 3, let's say in this example from 3 to 2, it will need comparatively less time to process the to process the data, to process the original data, as well as to make a model. Okay, so this is the advantage, means we can reduce the dimensions of the vectors so that we can process them in quicker time with lower computational resource availability. Okay, not every one of us will have not every one of us have the GPU. No? Most of us are working on CPUs, 12 GB, 16 GB RAM. Okay, a simple CPU is there, no GPU is there. No? So that's why this PCA this is the one of the reason. Second reason is that it actually reframe this original data X into more informative way according to their variance. Okay, let's see. Okay, it is just a more compact representation, you can say. It is you need some information to represent this data X, okay, which is 3 dimension. And in after PCA or KL transform, you can represent the some closely the same data with less number of information. Okay, it is, so you can say that it is more compact representation. Okay, so now let's see how we can apply, how we can now question is how to find this. Okay, so let's start. So let's say we have originally n dimensional data Rn, okay, and we want to convert this into Rm. So x is there and we want to convert them into x prime. Okay, x is basically the set of vectors, x prime also the same set of vectors, and let's say but the reduced dimension following this condition. It can be equal to n also, there is no issue. Okay, so but in that case, if m is equals to n, but in that case there is no meaning of because the same number of information is there, so why means the same computation will require. Okay, so there is no need, it is better to take m less than m. Okay, okay. Now what we do first, see, so we have these vectors, let's say vector x1, x2, x3, okay, and let's say x4. We have these four vectors. You can create even if we have one vector, there is no problem. Even if we have more than one vector, there is no problem. Okay, one vector, I think in that case there we cannot there is no meaning of calculating the reducing the dimension, so it is better let's say we have four vectors. So what these four vectors are there? These four vectors, hai, some real valued numbers like this. Okay, some vectors is given to you. For better understanding, let's say we write something like this. Let's say x1 is 1, 3, 4, minus 2, 4, 8, 0, 3, 9, and let's say another is 2, 4, 1. Okay, so this set of vectors x1, x2, x3, x4 is given to you. X1, x2, x3 and x4 is given to you. Okay, so first step is first step is to compute the mean of these vectors mu x. So I am not computing the mean of all four, but I will tell you the procedure so that you can easily compute. Otherwise this video will be too long. Okay, so first component will be 1 plus 4 plus 2 divided by 4. Okay, similarly second component 3 minus 2 plus 3 plus 4 divided by 2, and the third component will be 4 plus 8, 8 plus 9 plus 1 divided by 4. Okay, so you will get some value. Okay, you will get some value. Let's say you are getting a1, a2 and a3. Okay, okay, this is the mean vector you will get. So what will be the dimension of this mean vector? Is also 3 cross 1. Okay, now what you do, you compute the covariance matrix. Covariance matrix. Okay, what is the covariance matrix? Covariance matrix is nothing but sigma, this is equals to expectation of x minus mu x, x minus mu x transpose. Okay, so it will be something like this. Means how many vectors are there? 1 by 4 vectors are there, summation xi minus mu x, because these all are basically, I can say xi, where I is varying from 1 to 4. Xi minus mu x, and this is also xi minus mu x transpose. Sorry, it is bracket. Okay, so I have to do this operation. See, first you do this operation, means you subtract 1, 3, 4 from a1, a2, a3. Okay, you will get, what is the what dimension vector you will get? 3 cross 1. Okay, now if you take the same result and transpose this vector, so what will be, you will get 1 cross 3. Okay, 1 cross 3. Now you take the product. Okay, remember carefully. So this is the summation sign. Okay, this is the sigma, this is summation sign. I is equals to 1 to 4. Okay, this is the sigma xx, let's say sigma x basically. Okay, so see what we have to do. We have to compute this x1 minus mu x, x1 minus mu x transpose first, then x2 minus mu x, x2 minus mu x transpose, x3 minus mu x, x3 minus mu x transpose, x4 minus mu x, x4 minus mu x transpose. Okay, so what you will get actually in all the 4 cases, you will get a 3 cross 3 matrix. Okay, 3 cross 3, 4 such matrix you will get. Okay, now after 4, this what you do, you, let's say you are getting 4 matrix a1, a2, a3 and a4. Okay, sorry if I reuse any symbol, but you understand, because it will be difficult to make separate symbols for everyone. Okay, now after this what we have to do, we have to add all these matrix. So you add all this. Okay, after adding, what you have to do, you have to divide each entry of this matrix by 1 by 4. Why 4 is there? Because 4 vectors are there. Okay, so what size matrix you will get from this thing, this overall operation, is you will get actually 3 cross 3 matrix. That is actually nothing but your covariance matrix. Okay, this is the one thing. Now in maybe next video I will tell you more detail, because covariance matrix is containing so much of information. Okay, but in our next video I will cover the more detail of covariance matrix. But in this video, let's complete the KL transform first. Okay, so let's say I am getting this covariance matrix, something like this. What symbol I can use? Let's say for simplicity I am getting this covariance matrix DF GH I. Let's say prime also, to avoid any confusion. Okay, this is the covariance matrix. Now what you do after this fourth step is to compute eigenvalue and eigenvector. Okay, eigenvalue and eigenvector. So how many eigenvalues you will get? Let's say lambda 1 is the highest one, lambda 2 is the second highest, and lambda 3 is the lowest eigenvalue. Obviously you will get 3 eigenvalues, correct? Because 3 cross 3 matrix are there, so you will obviously get 3 eigenvalues. And correspondingly, for lambda 1 you will get an eigenvector, let's say v1. For lambda 2 you will get v2, lambda 3 you will get v3. Okay, so this thing you obtained. Now carefully notice all these things. Okay, So eigenvalues, eigenvectors you have computed from the covariance matrix. Now fifth step is what? In fifth step, what you will do, you make a transformation matrix. Let's say the transformation matrix is T. Transformation matrix. Okay, transformation matrix is T. So how to form this transformation matrix? Transformation matrix is this. The first eigenvector, take the transpose. Okay, means these columns eigenvectors v1, v2, v3, you arrange these as in a row form. Okay, v1 column vector and transpose become, means you have to arrange like this, v2 transpose and v3 transpose. So obviously what will be the size of this transformation matrix is also 3 cross 3. Okay, 3 cross 3. Is it clear? Now sixth step. Sixth step is, so you obtain the transformation matrix. Now you have to apply input data to this transformation matrix. Okay, okay. So see, one doubt may be possible there. If here, what is the dimension of the data? 3 cross 1. Okay, so obviously you will actually, if this is n cross 1, if the dimension is n cross 1, then this transformation matrix will also be n cross n. Okay, n cross n. Okay, so this thing. Now sixth step is to apply this transformation matrix. Apply this transformation matrix to the vectors of the original matrix or vector set x1. Why I am saying original matrix is, see, you can assume this 4 vectors as an image also. Like, correct na? I can assume like this. I am taking the columns of this image and separately making them vector. I can assume this is the image. Okay, image. Okay, so now what you do, you take each of this xi and subtract it with mu, like this, xi vector minus mu mean vector which we obtained. This is our mean vector which we obtained, this one. Okay, this one. Okay, xi minus mu x, and what you will get, what you will get actually the transformed output, let's say yi vector. So let's verify. What is the dimension of T? Dimension of T is 3 cross 3. What is the dimension of xi vector? 3 cross 1. Mu x is also 3 cross 1. So what you will get? 3 cross 1. Okay, so what will be the dimension of yi? 3 cross 1. Okay, these two things should be same for multiplication, and the output dimension is given by this. Okay, always remember, if you forget, always remember these two exterior values. So this will be this, right? So now you must be wondering, so we are getting the same, xi is also 3 cross 1, but yi is also 3 cross 1. So what is the meaning of transforming? Means if this is 3 cross 1, if these vectors are 3 cross 1 of size, now this also are where we are getting 3 cross 1. So how to get like this 2 cross 1? So you can do this by doing the truncation operation. See, now what I will do, seventh step. So this is the one thing, okay, but before, let's say I am not using sixth step right now, so ignore this. Now sixth step is this. What you do, from this transformation matrix which you obtained, you only take, let's say, first two eigenvectors. So what is the size? 2 rows and 3 columns. Okay. Now you use this T prime, let's say T prime modified transform matrix as a transformation. So yi will be T prime xi minus mu x. What is the dimension of T prime? 2 cross 3. What is the dimension of xi minus mu x? 3 cross 1. So what you will get? 2 cross 1 vector. So this is nothing but the reduced dimension of the corresponding vector x1. Okay, xi. So now you have, if you have four vectors xi, x1, x2, x3, x4, so you apply this equation 4 times. Okay, 4 times. So what you will get? 4 vectors, y1, y2, y3 and y4. Here the dimension of each of these vectors is 3 cross 1. Here the dimension will be 2 cross 1. Okay. Now I have to reconstruct this. Okay. Now I have to reconstruct this. So how I will reconstruct? Okay. So this is not a step. Okay. So 8th step is reconstruction. So from this equation, actually you can reconstruct. Looking at this equation, so you have to reconstruct this xi. Okay. So let's say xi will be, I am saying xi prime instead of xi. It is approximately, it is equal to t prime transpose. I am taking this t prime to the left hand side. Okay. So because t is this basically is formed using the eigenvectors of the covariance matrix. So those are orthogonal matrix. T is nothing but the orthogonal matrix. Orthogonal matrix. Okay, if you invert this matrix now, so orthogonal matrix, it's, let's say T is orthogonal matrix, then if you take the inverse of this matrix, so it will be T transpose. Okay, so this is the thing. So xi prime T prime transpose. Okay, T prime is moved toward left hand side multiplied with yi. Okay, then this plus minus mu x is still remaining on the right hand side, so bring this to left hand side, so it will be plus mu x. Okay, so now let's see the dimension. T prime is of T prime transpose will be of dimension 3 cross 2. Correct, because 2 cross 3 is T prime, so T prime transpose is 3 cross 2. Then yi is what? Yi dimension is 2 cross 1. 2 cross 1. What is the dimension of mu x? 3 cross 1. So what will be the dimension of reconstructed xi prime? Is 3 cross 1 plus 3 cross 1. This you will get actually nothing but 3 cross 1. So always remember, the reconstructed feature vector, original feature vector, and the reconstructed one and the original one will have the same size. Will always be have a same size. Okay. Now let's quickly, for complete understanding, let's quickly write here in, let's say I can use a different pen. different color. I don't know how to pick different color. Oh no. Okay. Okay, let's say if I do with if there is any color option is available. Okay, I think let's try to do this. Now if I ignore, let's say what actually I am doing, I am just starting with this step again. Okay, I am starting with I am actually starting with this step again. Okay, so see, if my T double prime, now I am, if I ignore this V2 transpose also, so what will be the dimension of T prime? It will be 1 cross 3, 1 row 3 column. Okay, means I am ignoring V2 transpose and V3 transpose, these two vectors. Okay, these two rows. So I only get T double prime as a new transformation matrix, that is nothing but V1 transpose of size 1 cross 3. So what will be the size of yi in that case? T double prime is 1 cross 3. This is 3 cross 1. So you will get actually a 1 cross 1 yi. Means from 3 dimension, now your yi is representing the 3 dimension information in 1 dimension. Okay? In this case, it is 2 cross 1, means 2 dimension, from 3 to 2. But if you ignore another one, V2 transpose also, then your yi will represent only 1 dimensional value for one vector. Okay, so you will get something like this. So y will be in that case, in T double prime case, will be 1 cross 1. Okay, so T1 transpose is what? 3 cross 1. 3 cross 1, yi is 1 cross 1. Plus mu x is 3 cross 1. So you will also get the 3 cross 1 vector in the reconstruction case. Okay. Now question arises, how many vectors I should pick, how many means this in 6th step, how many vectors I ignore, or in 5th step basically. How many V1 among V1, V2, V3, how many vectors should I remove? Okay, so in that case we will see there is a concept of mean square error. Up to how much error is acceptable to you? Okay, that we will discuss in our next class of this transform. Okay, if you like this video, so please like, share and subscribe, and hopefully hopefully you understood this concept. This is very important concept. People knows it, but how to apply this on a real time features, vectors, some people don't know. So after this video they are able to find the PCA calculation of the different set of vectors. Okay, so thank you very much. We will see you in next video.